In 2008, the Wood Buffalo Environmental Association adopted a very science-driven approach to monitoring and measuring the environment in the Athabasca oil sands region. One of the ways we are doing this is by monitoring pollutants along the pollutant pathway. In other words, from emissions, from the time they're emitted as dust or gases, all the way to their eventual fate and uptake, deposition to terrestrial ecosystems. In 2011, WBEA conducted a very, very extensive survey of forest ecosystem health in the region. And we had a team of 5 university or research institute agencies who did this work for us under our oversight. We collected an awful lot of soil samples, vegetation samples, atmospheric deposition samples during this 2-month campaign. And of course, once one collects all of these samples, it's very important that they're analyzed in a very high quality, quality assured, quality controlled manner using absolute state-of-the-art technologies. One of the first things we looked at was the concentration of the major nutrients, as well as many of the trace elements that are found naturally in forest soils, in order to determine were there more or less of these elements in the forest soils at any of our 21 forest health plots that we could then relate back to industrial emissions. The organic soils, that's the layer, the topmost layer of forest soils. And the cycling of nutrients within this, through the decomposition of litter, foliage that falls from the surrounding trees or vegetation, is absolutely essential for a healthy ecosystem functioning. The soils were collected by Dr. Sue Grayston, University of British Columbia. She returned them to her lab in Vancouver, and she is conducting, using gas chromatography techniques, a very high-level assessment of the phospholipid fatty acid assay for us, which we will then use to determine the relative state of organic matter microbiological populations at all of these forest health plots. Many of these are very, very time-consuming. For instance, it will probably take at least a year from the time of collection, perhaps a year and a half, until we have all of the quality assured, quality controlled results. Along with collecting the upper layer of soil, we also collected over 1,600 samples of the mineral soil, which is the next layer down, all the way down to the parent material. And one of the things that WBEA is charged with is looking for and documenting any long-term trends in soil acidity, soil nutrient status over the very long term, and how that might be related to industrial emissions in the region. So we will be able to compare the nutrient status of the mineral soils, not only amongst the plots, the 21 plots in 2011, but actually be able to look backwards and look at any of the change that has occurred in concentrations of these major and macro elements and soil pH by comparing our data to data from the same plots in 2004 and 1998. The Alberta government has an acid deposition framework in place in which we report these data so that they can determine if, for instance, the indicator that is used, the base cation and aluminum ratio, has it reached a certain level that might require mitigative action through pollution abatement. So it's used in both a scientific and a a policy application regulation sense. We were then able to adopt the source-receptor approach to understanding the effects that air emissions from industrial operations might have on the surrounding terrestrial environment. One of the tools we're using, which is well proven, is stable isotopes, which allows us to determine the fate of these industrial emissions to air across the landscape. In other words, if we measure the concentration of sulfur in foliage or in soil at one of our forest health plots, through the use of stable isotopes, analyzing these materials for the ratio of the different sulfur isotopes, we were then able to interpret what proportion of that sulfur is coming from man-made sources versus what's there naturally in the soil and vegetation. The work has been completed by Drs. Bernard Meyer and Bernadette Promsey at the Stable Isotope Laboratory, University of Calgary. This obviously, by its nature, requires some very, very sophisticated instrumentation and technology. There are a large number of steps involved to extract the individual isotopes out of the soil vegetation media. But in the end, once the extracts are prepared, they are eventually, the ratios of isotopes are eventually analyzed using mass spectrometry techniques. The stable isotope work in conjunction with the source receptor modeling work will be used by our scientists and WBEA to, I believe, for the first time in a scientifically defensible way, determine what is the air emissions footprint in the Athabasca oil sands region. One of the ways we're trying to integrate the fate of emissions, air emissions across the landscape, is through source receptor modeling. One of the tools we've used as the basis for this are lichens. Lichens are well established, well published on as an excellent biomonitor and have been used throughout the world. Biomonitors are organisms that are used to tell us something about the state of the ecosystem within which they grow. Lichens have also been used extensively to map the concentrations of sulfur and of heavy metals like arsenic, like mercury, across the landscape. In 2008, WBEA collected 2 lichens species from 359 sites in the Athabasca oil sands region of northeastern Alberta. We collected lichens at sites very close to the industrial emissions and at increasing distances away from the emissions in the north, east, south, and west directions. Actually, a number of our plots were considerably into Saskatchewan. It's a very huge undertaking. I believe it is the most extensive survey that has been done to date using lichens in the oil sands region. The lichen samples that were sent to the 3 laboratories in Research Triangle Park were then subdivided because each of the labs specialized in a particular analysis. The advantage of having sufficient material that could be subdivided and a portion archived for the future is that, of course, all 3 laboratories, regardless of what technique they're using, are analyzing the same samples. Trace element analysis was completed at Dr. Eric Edgerton's laboratory, Atmospheric Research and Analysis in RTP. Lichens were prepared there. In order to prepare them for analysis, they were actually digested using acids in a microwave oven system. Once the preparation was completed, a small sample was then used for analysis of sulfur, nitrogen, many of the other macro elements, calcium. This analysis was completed by X-ray fluorescence, which is a technique commonly used for that. And one of the advantages of X-ray fluorescence, unlike other techniques, is the materials being analyzed are not destroyed. They can be stored, they can be archived for future analysis, should we ever want to come back and analyze them again. In this process, they're looking for concentrations of 43 trace elements, such as selenium, arsenic, lead, vanadium, nickel. What are the concentrations of these 42 trace elements at the part per trillion level in these lichens that were collected in 2008? As well as using X-ray fluorescence technology, Mike Fort in Dr. Edgerton's lab also used robots to weigh the samples, and final analysis to trace level was completed using inductively coupled plasma mass spectrometry. The second set of analysis of lichen chemistry was completed by Dr. Joseph Graney of Binghamton University, New York, and they were completed at the U.S. Environmental Protection Agency National Exposure Research Laboratory in Research Triangle Park. Dr. Graney's focus was the analysis of lead stable isotopes, both in source materials we provided to him and the source receptor team, as well as stable lead isotope analysis in the lichen samples. The work of Dr. Graney and their source receptor team has brought an enormous amount of new knowledge to the stakeholders at WBEA. Through the use of stable lead isotope chemistry and ratios in source materials, such as raw oil sand, upgraded product, tailings pond dikes that contain the tailings ponds, natural dust, mine roads, Highway 63, and relating that to the lead isotope ratios in the receptor material, the lichens. Dr. Graney is able to complete, with his team, source apportionment study. Source apportionment is used to attribute concentrations of heavy metals in a lichen at point X on the landscape back to source type. In other words, what we have found through Dr. Graney's work is that stable isotopes of lead are an incredibly powerful tool for sorting out on the landscape what sources, natural or man-made, are contributing to the concentrations of trace elements and sulfur that we've measured in these lichens. The work of Dr. Graney and this source receptor team is now going to become very instrumental in identifying which source types, not the individual plants, the individual companies, but which source type are contributing to concentrations of sulfur, heavy metals that we measure on the landscape. The reason we are doing this is not only to generate new knowledge, scientific publications, report back to members, but these data, these results, will be extremely important to support environmental impact assessments and also to inform stakeholders, such as government regulators and industry, on what are the most important sources contributing to the movement of pollutants across the landscape. The fate of polycyclic aromatic hydrocarbons in the oil sands region have recently been the subject of much scientific investigation and public discussion. Some polycyclic aromatic hydrocarbons, or PAHs, are known carcinogens. So one of the value-added pieces of work that we wanted to do with the lichens we had collected was to analyze them for a large suite of PAHs to see what concentrations were there out in the terrestrial ecosystems and whether or not there was any pattern in concentration with increasing deep distance from the major sources of air emissions. This work was completed by Dr. Bill Studebaker and colleagues at the Research Triangle Institute in RTP. Dr. Studebaker's colleagues, Keith Briggs and Jocelyn Deese Spruill, used gas chromatography techniques to analyze the extracted pHs from lichens to the part per trillion level. This is allowing us not only to determine what the concentrations are and whether they increase or decrease with distance, but use the species of pHs to actually inform us on whether these pHs are coming from natural sources, oil sands processing, or both. We believe that the work that WBEA does is extremely important, not just to our stakeholders, but to the citizens of Alberta and Canada. And big decisions have been made and will continue to be made on development in the Athabasca oil sands region. And it's very, very important for policymakers, decision makers, regulators to have the best available information, scientifically sound information, such as is generated now by our source receptor modeling, to make the best decisions they can on behalf of stakeholders.